Anyone would like to suggest? So let's try x1 plus x2 3/4. That's what I don't like. I like 1 over x, but I really don't like 1 over x plus 1. Right? This could be simplified, this cannot. So let's give it a shot and say that this is y. As long as this dy is in the problem, then I'm okay. If dy is not in the problem, then I have to go back to the drawing board. Can anyone give us dy?
Is it 3/4x to the power 1/2 dx?
That's it. Awesome. Do I have it? Of course I do. 3/4, 4/3. Here it is. This is all dy. And what is this? Y. Do not copy the limits of integration, please. So 4/3 in front. Can anyone give us the integral?
Is it 1 over y dy?
Very good. dy over y. Now, when x is 1, how much is y? Anyone?
2.
Exactly. When x is 16, we have the 4th root of 16, which is 2. 2 to the 3rd, which is 8. 8 plus 1 is 9. Or you just plug it in. I don't like doing that, but that's okay. So 1 plus, we have 16 power, I always use parentheses, 3 divided by 4, and the answer has to be 9. If you have any doubts. Okay, good. So now, final step. We are not going back. It's a definite integral. So we have 4/3 in front. What function prime is 1 over y? Of the absolute value of y from 2 to 9. And you could say, but this is redundant because you have positive values here. True, but I have to write it first. So 4/3, natural log 9 minus natural log 2, which can be condensed, if you want to, into natural log of 9 over 2. Any questions? Any questions about the substitution?
I have one question.
Yes, anything.
Just to make sure, how do you change the endpoints once you start evaluating it?
So the integral is in x, which means x is from 1 through 16. But I created a new function. This function cannot be between 1 and 16. If x is 1, 1 plus 1 is 2. If x is 16, I get 9. Since these are now the limits of integration for y, from 2 to 9. The limits for integration for x are between 1 and 16. I cannot copy 1 and 16 here once I have a different function, which is y. I have to copy the limits of integration for that new function. So when x is 1, I get the 2. So the lower limit gives us the lower limit for y. So the upper limit for x will give us the upper limit for y. So when I plug in 16, I perform the calculations and I get 9.
Okay. All right, thank you.
You understand why, right? Because this is a totally new function. I can't copy the limits of integration for x, move them to y.
Yes, I understand why.
Very good. Other questions for me? Okay, so what I would like to do now is go back to those two topics that they are from pre-calculus, but I still want to review them with you in calculus. So when it comes to slant asymptotes, and the other one, which is not related to this, is holes in the graph. Hole in a graph, or holes in a graph. So let's start with the slant asymptote. So the slant asymptote is typical to rational functions of what I like to call type 3. What is that type 3? It's a rational function that has a higher degree in the numerator by exactly 1 unit higher. So I'm going to write that down, but I want to share my screen again so we can choose. So this is in chapter 4. Sorry guys, I didn't mean that. I meant this. So I never learned how to go from one chapter to another. What do I need to do? I have to go back to, how do I go back to some other chapter, not 5?
So Professor, I think you would put that X below search discourse. So it's on the, yeah, click that X. I don't know, click the X below that.
You gotta be signing as your session agenda.
Oh no.
Start searching the book again.
Okay, well now I have to find my keyboard because I can't reach because of my devices here. Okay, what is going on? So am I still logged in or I'm not logged in?
You're not logged in, you have to re-log
I'm not logged in, fine. I have to reach my, sorry for 1 second, I have to get my keyboard because I can't reach my computer, so what am I doing? But it always happened that I couldn't go back to the different chapter, I don't know why. Okay. Okay, I guess. Oh, good. So I want to go to chapter 4 in section 4.6, 4.5. Okay. Ebook, finally. Chapter 4, okay, I'm back. Right here. Slant asymptotes. Okay, so we are looking for functions, and I'm going to put this in right in a moment. We're going to look for functions with a higher degree in the numerator, rational functions of course, with a higher degree in the numerator than the denominator by exactly 1 unit higher. Exactly 1 unit higher. And they are towards the end somewhere here, they should be. Yes, here they are. Find an equation of the slant asymptote. Use a guideline, so I prefer something like this because I want to show the entire thing from the beginning till the end. So maybe 70, which has a higher degree in the numerator than the denominator, maybe 71, maybe 72. 72 is a nice one, looks nice, I don't know. This is not rational, this is not rational.
Can we do 72 then?
Okay, very good. So let's look at 72. So I'm going to copy x to the third over x plus 1 squared. Okay, I'm going to stop sharing. So now, this is what I like to call type 3. Type 3 has degree n plus 1 over degree n. These functions do not have a horizontal asymptote. So such a function does not have a horizontal asymptote, but a slant asymptote. What's the difference? Well, a slant looks like this, and a horizontal looks like this. So they will have something like this as an asymptote, not horizontal. There is no rational function that has horizontal, pure rational function that has horizontal and slant. So this type, with a higher degree, exactly by 1 unit higher than the denominator. If this is 2, this is 3. If this is 5, this is 6. If this is 10, this is 11. So higher in the numerator by 1 unit, it will have a slant asymptote rational function. Okay, so let's go through the whole steps, everything. This is a good review for the final exam anyway. So that's my page 9. So let's start with the table. F prime, f of x, and the second derivative. Can anyone give us the domain of this function? I'm going to copy it here again. So I can put it away. So, can anyone give us the domain of this function?
Is it all real numbers except -1?
Excellent, thank you. So when I plug in 0, obviously I get 0. So there is no discussion that x equals -1 is a vertical asymptote. I need to determine the limits, and I need to determine the limits. There is nothing else about the function. I'm done with the function. I'll move on to the first and the second derivatives in a second. So I want limit as x approaches -1 from the left, and limit as x approaches -1 from the right. Because I need to put them in here. Good. So can anyone give us the answer? Of course, the numerator is negative and the denominator is 0. Same thing here. The numerator is negative, the denominator is 0. So what will be the answer? We know the answer. That's not a big deal. But I don't know the sign.
Negative infinity?
Yes. And same thing, because the denominator, no matter what, is positive. And the numerator, no matter what, is negative. So both are negative. Good. So now let's establish that. Limit as x approaches -infinity from x cubed over x plus 1 squared. And then limit as x approaches positive infinity from x cubed over x plus 1 squared. Well, let's say I don't know, infinity over infinity. I apply L'Hopital's rule. Limit as x approaches -infinity. This is 3x squared over 2 times x plus 1. I continue. I should have not written that in here. Sorry about that. So limit as x approaches -infinity. It's still infinity over infinity. So it's 6x divided by 2. I will simplify, and what do I get?
3x?
Yes, but when x approaches -infinity, yes, it's 3x, but what do I get? That's it. And for the other one, I will have exactly the same, but infinity. So -infinity and infinity. Good. So now let's look at the first derivative. See what we learned about that from the first derivative about the function. So let me stop my video.